What if I told you there's a nuclear reactor designed to be inherently meltdown-proof? Forget the cooling towers and complex emergency systems. This isn't your grandparents' nuclear power. Discover the revolutionary Pebble Bed Reactor, a self-regulating marvel that literally can't melt down, even in a worst-case scenario. Could this be the ultimate fail-safe for our energy future? To understand why the PBR is so important, we have to look back at the accidents that have defined nuclear energy: Chernobyl, Fukushima. These disasters cast a long shadow, and they all share a common failure mode rooted in the design of traditional light water reactors. Traditional reactors rely on water under immense pressure to act as both a coolant and a moderator. If you lose that coolant, the remaining heat in the core to decay heat can't be removed fast enough. The fuel rods overheat, the zirconium cladding begins to burn, and eventually, the core melts into an unstoppable radioactive mass. The risk isn't about the nuclear reaction itself. It's about the engineering failure to manage the aftermath. If traditional nuclear carries this fundamental dependency on active, human-controlled cooling systems, is there a better, fundamentally safer way to get power from the atom? Enter the Pebble Bed Reactor, a concept pioneered in the 1960s, but finally reaching maturity today. Its name tells you everything. Instead of long metallic fuel rods, the PBR uses Triso fuel pebbles. Imagine a fuel element the size of a billiard ball. At its heart is the enriched uranium, but this core is encased in 3 layers of ceramic and high-density pyrolytic carbon, all sealed within a graphite sphere. This coating is literally the containment vessel for the radioactive material. Thousands of these pebbles are simply loaded into a large, graphite-lined tank, which forms the core. Instead of pressurized water, the coolant is inert, non-corrosive helium gas. Now, for the critical difference, the physics that makes meltdown impossible. The key is what is called inherent safety, and a property known as the negative temperature coefficient of reactivity. If a traditional reactor overheats, the nuclear chain reaction increases, creating more heat, a positive feedback loop. In the PBR, it's the opposite. The fuel is embedded in graphite, which acts as the moderator. If the temperature goes up, the distance between the fuel atoms slightly increases. This slight change means the fission neutrons are less likely to hit another atom to continue the chain. In plain English, as the core heats up, the reaction automatically slows down. It self-regulates. You can literally turn off all cooling, and the reaction simply stops itself. But what about that decay heat? The heat that melted Chernobyl? Because the core is dispersed and cooled by helium, even if all systems fail, the heat simply dissipates through the large surface area of the core vessel into the surrounding soil and air. The fuel itself is the final barrier. The Triso fuel pebble can withstand temperatures up to 1,600 degrees Celsius without breach. In a worst-case scenario where the helium is completely lost, the core temperature naturally peaks at around 1,200 to 1,300 degrees, well below the failure threshold. It can't melt down. It just gets warm and stops reacting. The Pebble Bed Reactor represents a profound shift in nuclear philosophy, from active safety systems that have to work perfectly to inherent safety built into the very laws of physics. They also operate at higher temperatures, making them ideal for efficient hydrogen production and industrial heat, not just electricity. It has a design that could finally give nuclear power the ultimate fail-safe we need to power a clean, sustainable future. Let me know in the comments, would you feel safer living next to a Pebble Bed Reactor? Don't forget to like and subscribe, and I'll see you in the next one.